Welcome to what will probably be a fairly short little video on solutions and x-intercepts. This is a super useful concept for the future. It's a good spot in the study of Algebra 1 to look at it, and you will see this come up in the future a lot as you move ahead in math. So it's a neat little thing. Don't forget to like this video and subscribe to the channel for more math help. Drop a comment. Let me know what you think. So the question here is, how do graphs of equations connect to solutions of equations? One of the things that I say a lot of time in my own math classes is math is consistent, the ideas are connected. So what we don't want to fall into is this trap of thinking that graphing equations is one skill and solving equations is this totally different skill that has nothing to do with the graphs. All of these concepts are interrelated, and when you can grasp how they are interrelated, it opens up whole new possibilities for how you visualize and understand the math and what you can do with it. So as a little introductory idea here, on the x-axis, the y-coordinate is always 0. So take a look at this. I did not do every single point here because it would have gotten too crowded. But when you're on the x-axis, if you were to take any one of these points and look at the coordinates for those points, the y-coordinate of those points is always 0. So we have a dot there at -9, 0. Right here, this is -5, 0. My origin is 0, 0. We have here the point 3, 0. We have 7, 0. And I could pick points in between those points. I could say 2.5, 0. And what you really want to notice is that the y-coordinate of all of those points is always 0. And so we're going to just draw that connection between the y being 0 and the x-axis. Okay, so pause the video if you need to, just to let that idea sink in, that the y coordinate of all of those points is always a 0. Now, consider this equation. We're going to solve this algebraically. So this is a great review of our equation solving skills. And the way I usually present this is we're going to simplify the left side and we're going to simplify the right side. And we're going to do that separately. We're not going to marry the two sides together. Okay, we're going to simplify the right side and the left side separate from each other. That simplification will involve some distribution. So on my left-hand side, I'm going to go ahead and distribute that 4. And you might want to change that to plus a negative x, negative 8. And on the right side, we're going to go ahead and distribute that 3. And on the right side, everything is as simplified as it's going to get. I can do a little bit more on the left side because I have some like terms here. So 3x plus 4x is 7x. And now I have simplified each side as far as it can go. And notice that I also did that in different colors because I really want to emphasize, like, okay, we're keeping that separate. Now that I've got each side separately, now I'm going to look at combining the sides together, or I shouldn't probably use the word combine there, but we're going to consolidate them and start marrying them and doing stuff on each side. So on the left side, I have 7x minus 8. On the right side, I have 3x plus 12. And I am going to consolidate my x's by subtracting 3x from both sides. 7x minus 3x is 4x. And then 3x minus 3x is 0. That is why that cancels out, because 3x minus 3x is 0, leaving me with just the 12. And then I am subtracting 8 here, so I'm going to go ahead and add 8, but I have to do that to both sides. And again, notice we're not doing the same thing to both sides until I've already simplified each side. Okay, negative 8 plus 8 is 0. Okay, and that's why they cancel out. 12 plus 8 is 20. And then this is multiplication between the 4 and the x. So we'll divide both sides by 4 and we get x is equal to 5. And that is our algebraic solution to that equation. That notice, I'll just re-emphasize that top to bottom. Okay, every step follows from the step that comes above it. And if anybody were to ask you, where did you get a 12 from? You should be able to explain where you got the 12 from. Where did you get a 4x? Well, what did you do to get the 4x? Nothing should be like confusing or voodoo or magic or anything like that. All right, now we're going to set the equation equal to 0. And I didn't want to throw out that terminology without defining it. Sometimes math teachers can do that. We can just say set equal to 0 and we assume everybody knows what we're talking about. To set something equal to 0 means to manipulate the equation so that there is a 0 on one side of the equal sign. So the set means like do some stuff to it. The equation, that's the thing we're working on, equal to 0 means like I should see a 0 in there, and the 0 can be either on the left or the right. It just is like on one side of the equal sign. So for the most part, this is going to look the same. And so we're going to distribute, okay, and I'm going to combine my like terms. So we have 7x minus 8, okay, and I'm going to get all the x's to one side. So we'll subtract the 3x, and I'm aware that I copied something wrong there. Give me a second. Threw an x there, that should not be there. Okay, and right here, here's where we're going to do something different. So all of that work is the same as what I showed on the previous slide there. From here, though, instead of adding the 8 to both sides to try to isolate the x, I'm going to go ahead and subtract 12 from both sides. And this is where it might be nice to think of it as plus a negative. So this is negative 8 plus negative 12, okay? Negative 8 plus negative 12, which is going to give us a negative 20. And now I have this 0 on one side. Okay, so that's what we mean when we say set it equal to 0. So you just kind of take a little bit of a detour down at the end there. Now what we're going to do, and this might seem a little bit weird, is we're going to substitute y in for the 0. Okay, I'll underline that in a different color. We're going to substitute the y in for the 0. So instead of 4x minus 20 equals 0, I am going to go ahead and replace that 0 with a y. So that I have 4x minus 20 equals y. Now, I'm going to pause for a moment. Think back to the slide like a couple slides ago when we talked about the x-axis and how every single point on the x-axis, the y coordinate was equal to 0. So essentially what we're doing there is we're taking that 0 and we're saying, okay, we're going to make that y 0. We're going to make 0 and y equal to each other. So if you're a little uncomfortable with the 4x minus 20 equals y, you can, of course, say y equals 4x minus 20. And for some reason, I think I said 4x minus 0 equals y. I meant 4x minus 20 equals y. Or if you prefer, y equals 4x minus 20. All right, so that's what the graph looks like. So that is the graph of the equation y equals 4x minus 20, and the y-intercept is 20, and you can tell like if the line kept going down, your y-intercept would be down there at the negative 20. Now notice where the x-intercept is. X-intercept is right there. Okay, and that number should look a little familiar to you. We already knew that the solution to the equation was x equals 5 because we went and figured that out. Now we're actually able to see it on the graph. If you look at where the x-intercept is, it's equal to 5. When we made the substitution that 0 was equal to y, it was as if we plugged in 0 for the y coordinate, and then we used the graph to find the x coordinate. So if you think about what the coordinates of that point are, it's the point 5, 0. And back when we said, okay, take that 0 and plug in a y so that we're able to graph it, what we did was we were kind of saying, oh, we're going to isolate this particular point. So we're going to set y equal to 0, and then we're going to use the graph to figure out what the x value must be, and the x value must be 5. In summary, the solution to the equation is the x-intercept whenever you replace the 0 with a y. Okay, so that is a general principle that will hold true. So why is this useful? It gives us a graphical way to solve equations. So it means we're not restricted to the algebraic methods of distribution, combining like terms, isolating the variable. We are actually able to find a solution using a graph if a graph is the tool that we're more comfortable with. In higher level math, when you are allowed to use graphing utilities like graphing calculators or online resources like Desmos, this gives you another whole way to solve equations. Typically in Algebra 1, your use of graphing utilities is limited, but it does not stay that way. And by the time you get to, say, pre-calculus or calculus, one of the skills you're supposed to have is the ability to use a calculator and the features on the calculator. And so this would come in really, really useful if you had a graphing utility. And Desmos is a website that is free to everyone. So consider this equation. So this is a different kind of equation. You can tell because it's got an x squared there. And so we have not at this point in the sequence of lessons covered how to solve that. Now, if you're watching this video as, say, an Algebra 2 student or a much later Algebra 1 student, you'd be like, well, I know how to solve that. That's because we eventually cover it. But let's just say you didn't, or let's say you do, and you're looking for another way to check your answer. So we're going to take that equation and set it equal to 0. That means getting a 0 on one side. And I can do that if I subtract 14 from both sides. So on my left side, I'm going to have x squared minus 5x minus 14. On the right side, 14 minus 14 is 0. And now what we'll do is we'll substitute a y in for that 0. And again, that's the little step where we're isolating the x-axis. We're saying, okay, we're going to make the y coordinate a 0, and then the x-intercept should be the solution to the equation. Now, for this is a much, much harder equation to graph by hand than a line is. So a lot of people will use a graphing utility for this. I went ahead and generated the graph, and I want you to notice where the x-intercepts are. So we have an x-intercept at -2, 0, and again over here at 7, 0. And you might think, ooh, like, wait a minute, there's 2 x-intercepts? What kind of a shape is that? That's not a line. No, it's not a line. It's a different kind of equation, and it gives us a different kind of graph. But math is consistent, and the principles that work for lines are also going to work for this, which is why we don't take shortcuts. So the x-intercepts are -2, 0, and 7, 0, and so each of those give us a y and an x, and therefore the solutions are x equals -2 and x equals 7, and it turns out you didn't have to do any algebraic work at all. You could just get a graphing utility and graph it, and you can see the solutions. Now let's do a quick algebraic check of this. This you might not have done for a little bit, but we're going to plug in the values, and this is a great time to emphasize that the solution to equation is the value of the variables that make it true. So let's say you're doubtful. Oh, I don't think there can be 2 answers. Well, let's go ahead and check this out. So -2 squared, that is, I'm going to do a little bit of scratch work. -2 squared means -2 times -2, which will give me a +4. And right here, you might, instead of using the minus sign right there, you might want to say plus negative, and that will emphasize to you that is -5 times -2, and a negative times a negative is a positive. And then 4 plus 10 is 14, and that is a true statement. Therefore, the x equals -2 does check. And we're going to come over here and do the same thing with the 7. So we have 7 squared minus 5 times 7. 7 squared is 49. Then we have 5 times 7 there, which is 35. And 49 minus 35 is 14. And that checks. That is also true. And so there's actually two values of x that when you plug them into the equation will make the equation true. So the x-intercepts did check, and we know that those numbers do work in that equation. So you can actually solve any equation this way. It is really useful, especially when you're dealing with a kind of equation that you don't know the algebraic steps. This right here, like on this slide though, this is not a solution. This is a check for the solution. And every once in a while, my students will turn in work and they'll show me the check, but not the actual steps for the solution. So we don't want to confuse those. That was just a check. I had the solutions already, and we were just checking to make sure they worked. All right, did you find this video helpful? If so, please like the video, subscribe to the channel, drop a comment below, let me know what you think, and I will see you next time.